Good morning, students. Children, we have started with lesson number 4, Effects of Electric Current from Science 1. And in our previous videos, we have learnt about heating effect of electric current. So in today's video, we shall be learning a new topic. So, let's begin. Force acting on a current carrying conductor in a magnetic field. In 1821, Ampere discovered that when a current carrying conductor is arranged in a magnetic field which is not parallel to the field, then a force is experienced by it. So, this has been discovered by the scientist Ampere. So, what he says, a conductor carrying an electric current has a magnetic field around it. This magnetic field and the magnetic field of the horseshoe magnet affects each other. It is same as bringing two magnets close to each other. It makes the conductor move perpendicular to the direction of the magnetic field. Hence, when a conductor carrying electric current is placed in a magnetic field, it moves or it experiences a mechanical force. When the direction of the current is reversed, the magnetic field set up around the conductor also reverses and the conductor is deflected back. This principle is used in the working of electric motors. Fleming's left hand rule. Now, look at the figure. Arrange the thumb, forefinger and the middle finger of your left hand mutually perpendicular to each other. As you can see here. If the forefinger indicates the direction of the magnetic field and the middle finger indicates the direction of the current, then the thumb will indicate the direction of force on the conductor. Magnitude and direction of force. The magnitude and direction of force on a current carrying conductor depends upon the current I, intensity of magnetic field B, and the length L. So children, it means F is directly proportional to I, F is directly proportional to B, and F is directly proportional to the length L. Relating these three, F is directly proportional to IBL, or F is equal to KIBL, where K is the constant whose value depend on the choice of unit. In SI unit, K is equals to 1. Therefore, F is equal to IBL. Understood, children? So, this was the force acting on a current carrying conductor in a magnetic field. Now, let's see what is an electric motor. Electric motor is a device which converts electrical energy into mechanical energy. Let's see its construction. Electric motor has the following four main parts: the permanent magnet, armature, split rings, and carbon brushes. So this is the construction and it has these four main parts. Let's see the working of it. A direct current source is connected between two metallic brushes, that is B1 and B2. When current passes through the coil, it flows in arms CA and DB in a direction perpendicular to the magnetic field. Observe the figure carefully. Electric current is sent in a rectangular wire loop placed in a magnetic field. The magnetic field, due to electric current in the wire and the magnetic field of the magnet, repel each other. This causes a sideways force to be created in the wire. The force causes the wire to turn, and this is how an electric motor works. Let's see electromagnetic induction. Now in this video we shall learn about electromagnetic induction. The phenomena of electromagnetic induction can be demonstrated by an experiment. Wind an insulated copper wire on a paper or a wooden cylinder so as to form a coil in the form of a solenoid. Connect the two ends of the coil to a galvanometer and place a magnet close to it. The reading of the galvanometer is 0 when the magnet is stationary. Means the magnet is not moving. The pointer of the galvanometer deflects towards the right when the north pole of the magnet is moved towards the solenoid. The galvanometer shows 0 reading when the motion of the magnet stops. This proves that as long as the magnet keeps moving, current flows in the solenoid. If the magnet is moved away from the solenoid, current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the left. Now, the deflection increases if the magnet is moved away with greater velocity. If the polarity of the magnet is reversed and the magnet is brought close to the solenoid, then the current flows in an opposite direction. The galvanometer accordingly turns towards the left. Now what Faraday has observed? He has observed that current flows in the coil only when there is a relative motion between the coil and the magnet. The direction of deflection in the galvanometer is reversed if the direction of motion is reversed. Okay? Now, factors leading to increased current in the coil. First, by using a strong magnet, increasing the motion of the magnet and increasing the area or the number of turns of the coil. Now, according to Faraday, when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant. So, the galvanometer shows no deflection. Let's see what happens the next. But when the magnet is moved towards the coil or vice versa, the magnetic flux changes and an EMF, that is electromotive force, is induced in the coil. If the current is complete, the EMF causes current to flow through it. Now the position of the magnet and deflection in galvanometer. Magnet at rest, so there is no deflection in galvanometer. Faraday's law of induction. Whenever there is a change in the magnetic flux linked with a coil, an electromotive force, that is EMF, is induced. The magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linked with the coil. The direction of the induced EMF depends on whether there is an increase or decrease in the magnetic flux. Understood, children? Now, John Ambrose Fleming gave two rules to determine the direction of motion or the direction of induced current. So, he is John Ambrose Fleming. He gave, when the left hand rule is for electric motors, the right hand rule is for generators. According to Fleming's right hand rule, if the thumb, the forefinger and the middle finger of the right hand are stretched perpendicular to each other, then the thumb represents the direction of movement of the conductor. The forefinger represents the direction of magnetic field and the middle finger represents the direction of the induced current. Now the Lenz's law states that the direction of the induced EMF is such that it always tends to oppose the cause which produces it. Lenz's law obeys Newton's third law of motion, which states that to every action there is always an equal and opposite reaction. It also obeys the law of conservation of energy. It states that energy can neither be created nor destroyed. Therefore, the sum of all the energies in the system is constant. Lenz's law is based on Faraday's law of induction. Lenz's law states that when an EMF is generated by a change in magnetic flux according to Faraday's law, the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produces it. Understood, children? Now let's look at the summary. Force on current carrying conductor. Fleming's left-hand rule. A piece of wire held between the poles of the magnet. So when the current flows through the wire, an upward magnetic force acts on it. If the direction of either current or external magnetic field is reversed, then the wire moves downwards. Okay, children? Now, what does Fleming's left-hand rule states? Hold the thumb and the first two fingers of the left hand at right angles. The thumb gives the direction of magnetic force F. If the first finger points in the same direction as the external magnetic field B and the second finger is in the same direction as current I. Electric motor. Electric motor is a device which converts electrical energy to kinetic energy and commonly found in the electrical appliances. Electromagnetic induction. Electromagnetic induction is the process of using magnetic fields to produce voltage and, in a complete circuit, a current. Michael Faraday first discovered it using some of the works of Hans Christian Ørsted. His work started at the first using different combinations of wires and magnetic strength and current. But it wasn't until he tired moving the wires that he got any success. So, with this, we have finished our today's topic. Thank you, students, for listening to me. Children, please read the lesson after watching this video attentively to understand it more clear. Okay, children? I hope you all must have understood today's topic. So, we shall see you in the next video with a new topic. Till then, take care. Bye, children. Thank you.